In this video, I'm going to explain how to find a tangent plane to a parametrized surface at a point on that plane. So here we have the general formula for a parametrized surface R of uv, which equals x of uv, y of uv, z of uv. So we're going to fix our point uv. Okay, uv is going to correspond to the point on the surface where we want to find the tangent plane. Okay, so let's draw a picture of what we have. Without even looking at our surface yet, we can easily, just from our equation, our parameterization of our surface, identify two tangent vectors, right? So from this parameterization, we know that partial r partial u is going to be partial x partial u, partial y partial u, partial z partial u. And the derivative with respect to v is going to be partial x partial v, partial y partial v, and partial z partial v. There are infinitely many tangent vectors at a point on a plane, but let's look at these two and think about why the derivative with respect to u and the derivative with respect to v are tangent vectors to the surface. So here's our surface. Okay. So this is a surface in 3D space, and let's look at the place where this is. Let's say this is U, and we'll have this be V, and then we have this point here. This is our point UV. Okay. And then, so along my red line, let's let this be the curve where u is held constant and v is varying. Okay, so this vector here, so let's say that we're going this way. Let's call that R sub v. Again, the curve where u is constant and v is varying. So this vector that I've drawn is really a tangent vector to the curve where u is constant. And then let's draw our other tangent vector to the other curve. So maybe something like that. Oops. So this is really a tangent vector to the curve where v is constant and u is varying. So these two vectors are two vectors that are going to be in the tangent plane at this point uv. They do not point in the same direction if they are linearly independent, right? One is not a scalar multiple of the other. And if we have these two vectors, then we can use these two vectors to determine the tangent plane at this point uv that we're talking about. Okay? We say that a parametrized surface is smooth at uv. Smooth at uv if the derivative with respect to u, these r sub u and r sub v vectors are linearly independent. And if we are in three dimensions, then we have an easy way to check if two vectors are linearly independent. We just check their cross product and make sure the cross product does not equal 0. in other dimensions, we don't have a cross product, but you can still talk about vectors being linearly independent. So if they are linearly independent, then, well, then this cross product, which I'll call n, is perpendicular to both of the vectors we crossed. So n is perpendicular to r sub u, and n is perpendicular to r sub v. And this n vector is a normal vector to the tangent plane. So if we let r sub o be some given point on our plane where we are the point at which we're trying to find the tangent plane, if that is r of uv, then the equation for the tangent plane is n dot r minus r sub 0 equals 0, where n is our normal vector, the cross product of r sub u and r sub v. R is an arbitrary point in space, and this equation tells you when that point in space is on the tangent plane. So let's look at a few examples. In our first example, we want to find the tangent plane to the surface. Our parametrized surface is x equals u squared, y equals u minus v squared, and z equals v squared, where u and v are non-negative values greater than or equal to 0. And we want to find the tangent plane at the point 1, 0, 0, 1. You don't necessarily need to sketch a surface to find the equation of this tangent plane. So step 1. For step 1, we want to figure out that this point that we're given, x, y, z, is 1, 0, 1, corresponds to what point in the UV plane? Okay, so let's figure that out first. We have x equals u squared, which is 1. So that means u could equal plus or minus 1. But because we've already said that u must be a positive number, we know that u is 1. And z, which is v squared, is also 1. And again, v is going to be 1. And I'm just going to double check that these values work in the parameterization for y, which is u minus v squared. 1 minus 1 squared is 0, so that does confirm the point 1, 0, 1. And so I know that my UV point is 1, 1. Okay, so now let's look at our derivatives at this point 1, 1. So again, my parameterization, r of uv is u squared, u minus v squared, v squared. So the derivative with respect to u is going to be 2u, 1, 0. And then evaluated at my uv point 1, 1, I'm going to get 2, 1, 0. Now, partial v is going to be 0, negative 2v, 2v. And evaluated at our point 1, 1, I have 0, negative 2, 2. Oops. 0, negative 2, 2. Okay, now I'm going to find the normal vector, my third step, n. I'm going to cross those two vectors that I just found. So this is going to give me, so remember we have I, J, K, 2, 1, 0, and it doesn't matter what order you put these in because every tangent plane has two normal vectors to the same point, which would be scalar multiples by -1 of each other, so the order of those two rows won't matter. And I'm going to get 2 minus 0, 0 minus 4, and -4 minus 0. And so I get that my normal vector is 2, -4, -4. And of course, since you can scale this by anything, if you want to make the numbers simpler, you can make that 1, -2, -2 also. Or actually, I should write that as, let's be a little more specific here. And I'm just going to use 1, -2, -2. Okay. So we are now ready to take all of this and write our equation. I'm going to write it in linear form here. Okay, so we have our normal vector and we have our point. So we are taking those and plugging them into this equation that we have for the tangent plane. So this is going to be our normal vector, 1, -2, -2. R is some arbitrary point, I'll call it x, y, z. And then our r sub 0 point was 1, 0, 1. Okay, so that's going to give me 1, -2, -2 dot x minus 1, y, z minus 1. When I dot these, I'm going to get x minus 1 minus 2y minus 2z plus 2 is 0. Or x minus 2y minus 2z is -1. All right, so that is the equation to our tangent plane, the equation of our tangent plane to the surface at the point 1, 0, 1. All right, let's look at our second example. We want to find the equation of the tangent plane to the surface, x equals u cosine v, u sine v, or y equals u sine v, and z equals u. And you may remember from the lecture on parametrized surfaces that we could show that this is the equation for the parameterization for a cone, x squared plus y squared equals z squared. And we could prove that by getting rid of the parameters and writing an equation only in x, y, and z. So this is going to, here we're going to find the equation for a tangent plane at any point. A point is not specified, so we'll just say at the point x sub 0, y sub 0, z sub 0. Okay, so my r of uv, u cosine v, u sine v, u. Let's find the derivative with respect to u is going to be cosine v, sine v 1, and the derivative with respect to v is going to be negative u sine v, u cosine v 1. Oops, 0 with v. Okay, now we're going to cross those. And what am I going to get? I'm going to get 0 minus u cosine v. Then I'm going to get negative u sine v minus 0. And lastly, I'm going to get u cosine squared v plus u sine squared v. Okay, so let's simplify this. So our cross product, and remember our cross product is our normal vector, is negative u cosine v, negative u sine v, and I can factor out the u of this z component and get u times cosine squared plus sine squared, which is just u. And so now we have the equation of our tangent plane, which is normal vector. So, well, how do we, looking at this, if you look at the components of our normal vector and you look back at the original parameterization here, this is the negative of x, my first component. This is the negative of y, and this is z. So my normal vector is negative x, negative y, z. Okay, so that means my tangent plane is negative x, negative y, z. Remember, this is normal vector dot r minus r sub 0 equals 0. So dot some arbitrary point x, y, z minus wherever my r sub 0, which I'll just call x sub 0, y sub 0, z sub 0. Okay, so let's think about this. Let's look at a picture of our cone and think about what's going on here. So here we have a picture of our cone, and if we look at the normal vector, negative x, negative y, z, this normal vector is going to point upwards when z is positive, right? Because the z component is z. So when z is positive, this is an upward facing vector. When z is negative, this would be, the vector would point downwards, right? Now, remember that we said that in 3 space, we can confirm that 2 vectors are linearly independent if the cross product is not equal to 0. So here, if you look at our normal vector, when does this normal vector, which is the cross product of r sub u and r sub v, equals 0? And there is a point there. If x, y, and z are all 0, then the normal vector is 0. So what is going on at this point 0, 0, 0? So we're saying what this has is that the surface is smooth. Remember, that's what we were talking about. A surface is smooth if these 2 derivative vectors are linearly independent. This surface is smooth as long as the normal vector is not 0, so as long as we are not at the point 0, 0, 0. What we have here, this point at 0, 0, 0, this is called a singularity. Okay, and what's happening is the surface at this point 0, 0, 0 does not have a well-defined tangent plane. Okay, so the surface near or at the origin, we say it cannot be well approximated by a single tangent plane.